Okay, so coordinates of local maximum minimum points. So we know that we're trying to solve y dash of x equal to 0, because that will imply that we have local max or min. Okay, so we're just going to go ahead and solve it. So you recall from before that the gradient was given by e to the 3x, and that was 3x plus 1. So we're going to solve that equation equal to 0. We know that e to the 3x is always greater than 0, so that can't be any part of the solution. So we must get that by equating 3x plus 1 equals 0, so x equals negative 1/3. And therefore the y partner at this particular x coordinate is negative 1/3, and substitute it into here, 3 times by negative 1/3, and we quite quickly see that's negative 1 over 3e. So we know that the gradient equals 0 when x equals negative 1/3 and its partner y equals negative 1 over 3e. So I want to discover the nature of the stationary point, whether it's a local maximum, local minimum, and there is another possibility. It could be a local point, stationary point of inflection, but it tells us a maximum or minimum, so we maybe eliminate the point of inflection from our inquiry. I'm just going to draw a little sketch here. Okay, so when we have kind of a local maximum here, at this particular point here, at A, the gradient just before is positive, the gradient after is negative, and the gradient at A is 0. So the gradient at A is 0, before it's positive, and after it's negative. So if this is f of x, this is f dash of x. And then let's have a look at the second derivative as well, f double dash of x. So at this point here the gradient is negative. In fact, all the way along this particular f dash of x function the gradient is negative. So local maximum, when we feed a value of a into the second derivative, we should get a negative value coming out. Okay, so that's how we test if it's a maximum, and if it's a local minimum up here, so there's a local minimum here, then at this point of A here, the gradient before is negative, the gradient after is positive, and so therefore here, as you move along all of this function, the gradient is always positive. Okay, and if I extend this a little bit, we'll have a little look at points of inflection. Let's have a look at a non-stationary point of inflection, just for fun. So this is a point here, and it's a change of curvature. So just have a little think about this. Before this particular point, the curvature changes from concave down into concave up, so it's a change of curvature. But before, the gradient's positive, after the gradient's positive. At this particular point, the gradient's positive, but before the gradient is steeper, after the gradient is steeper. So this is what it looks like here. Yeah. So just before B, the gradient's positive, just after B, the gradient's positive. Yes, the gradient's positive before, the gradient's positive afterwards. For a local maximum minimum, the gradient goes from a positive to a negative, or a negative to positive. Okay. So this is going to help us with determining a point of inflection, and clearly at B as well here, the gradient at this particular point here is 0. So the second derivative equal to 0 implies that it could be a point of inflection. So negative here, and then positive afterwards. Okay, so that might help us. So let's get on with the second derivative and have a little look at it. So the first derivative, y dash of x, is equal to e to the 3x into 3x plus 1. So therefore the second derivative is equal to leave the first, differentiate the second, plus leave the second, differentiate the first. So if we know that we've got x equals negative 1/3, and that implies the gradient equals 0, so we want to know the nature of the stationary point. So we substitute negative 1/3 into the second derivative. Yeah, we have a look at the overall sign of the second derivative. If it's negative, then we are at a local maximum. If it's positive, then we are at a local minimum. So we just substitute in. So y double dash of negative 1/3 equals 3 into e to the 3 times negative 1/3, that's e to the negative 1, and that's 3 times negative 1/3 is actually negative 1, plus 1 is 0, so that'll just take out that second term. So that's actually 3 over e, so that's positive. So if we have positive here, then we know we've got a local minimum. So f double dash of x, I'm mixing my notation up here, so f double dash of x is greater than 0 at x equals negative 1/3. Therefore we have a local minimum. And we might as well just put the actual set of coordinates. Negative 1/3. What was that? Negative 1 over 3e. Is that right?